Alright guys, so what we need to do is create a robot soccer ball. The ultimate goal is by 2050 we want to be able to beat a human soccer team. So we've got to conform by the F180 rules. So we've been given an Android phone and we have to be able to convert this phone into a robot that can navigate to this ball while avoiding these obstacles.
Sounds good.
Let's do this!
Yeah!
To the sky from the bottom, living out the dreams that have all came true. Now I'm trying to reach to the stars from the heavens, never giving up like they thought I'd do. Though still I'm trying to reach to the sky from the bottom, living out the dreams that have all came true. Now I'm trying to reach to the stars from the heavens, never giving up like they thought I'd do. This is all I know, all I know, all I know, all I know. This is all I know, all I know, all I know.
I'm Tom, and I'm a member of the electromechanical subsystem working on the chassis design, along with the implementation of the accessory components, such as the dribbling and kicking systems. Utilising the latest 3D modelling software, the mechanical team was able to create a unique 3-layer design incorporating a horizontal foam placement with a down-facing camera slot. Through the use of a custom-cut front-facing mirror, the field of view can be adjusted as required, providing the optimal range of sight configured to suit the designated playing field. Driven by two 30:1 ratio micro-metal gear motors, the differential system is powered by a 7.2 volt dual-cell lithium-ion battery, providing sufficient power for the electrical systems. The nominated dribbling system comprises of a 3D printed cylindrical bar coated in a soft PVC material with silicon bands to provide a cushioned yet high friction tread. Optimal height positioning provides maximum applied normal force capable of grabbing the ball without compromising the 20% ball coverage rule. To the use of an adjustable band-driven pulley system, the dribbler bar is powered by a down-geared 9,000 RPM electric motor, providing a reliable 80 grams per centimetre of torque. Positioned at the front of the robot under the line of sight, the dribbler integrates seamlessly into the chassis, from the versatile laser cut mounting system through to the software trigger-enabled electrical ports, capable of toggling the dribbling system as required. Through further implementation, the proposed kicking mechanism is to be a solenoid actuator due to its simplicity yet broad range of kicking speeds. Incorporating a durable aluminium kicking plate, a high-strength 36-volt solenoid actuator is powered by an additional DC-DC boost converter, producing an adjustable output of actual 50 volts, capable of kicking speeds of up to a metre per second.
Hi, so my name is Janish and I was in charge of the electrical design of the team. So what I did is I designed a PCB board that would fit all our requirements such as size, functionality, and also being able to be cost effective. So firstly, I designed the PCB board on Eagle with extra components and spare header pins to allow the use of extra features if we need to. And from that, I managed to refine it down to a smaller, more effective PCB from this to this, which only put the necessary components on that we needed. As you can see, it contains a transistor. A transistor that allows us to switch our dribbler on and off depending on whether we need it or not, and a motor driver which allowed us to control both motors simultaneously quite well. As you can see, this PCB is the exact same size as the IO, allowing the IO to sit directly on top and allow us to have more space on the robot for other stuff such as batteries. The good thing about this PCB was that it also contains extra ports for analog and digital outputs, allowing us to use extra sensors designed on these breakout boards to actually do more features such as wall detection and other stuff. So what I also did is I also worked on the simulation part of this assignment to try and replicate an AI system. And what I did is I modified the existing simulation code to actually assume that we had a perfect dribbler which could successfully grab the ball and avoid obstacles, walls, and taking the ball to the goal. So as you can see with the simulation, what's happening is the robot hits the ball and then assumes it's grabbed it and takes it towards the goal and dunks it in. So what we've done, another step on this would have to be is to actually implement the actual dribbler as part of the code.
Hi, my name is Reese, and in terms of communication, we are using an IO OTG board for our Note 2 smartphone. To communicate with the board itself, we are using the Java programming language so that we can drive our motors and fully organize our external outputs and our sensory inputs. To drive our motors, a PWM controller Android application was developed. We purchased our IO, and we downloaded the firmware image zip file to find the API and the libraries necessary for the IO applications that we needed. Wanted to manipulate the peripherals. In one of the already existing IOI applications within the firmware image file downloaded, they were already manipulating the PWM signal for the onboard LED. This was prototyped with an LED on a separate breadboard, with a basic user interface of just one on and off button and a progress bar to determine the brightness of the LED. This code was later engineered to accommodate for 2 PWM signals for 2 motors, with 2 forward and reverse buttons and 2 progress buttons. And I'll just show you the user interface now. So we have our progression bar for motor 1 and our progression bar for motor 2, and these bars determine the speed. In other words, they determine the output given to drive the motors, and we have our 2 buttons. They don't specify as on and off, but as forward and reverse. Eventually, the PWM controller code was culled to change some of the pins for the motors on the yo-yo schematic itself, and to adjust certain variables in order for the code itself to be threaded in full system integration with the OpenCV code, as well as other things that the group members were working on.
In this section, we'll discuss the search algorithm for the robot. Some of the points that will be discussed include the solution to the problem and some of the problems that the group faced in this project. The task ahead was to successfully search for the ball. Many ideas were brainstormed, and the best idea was selected by the group. We thought that the best idea would be for the robot to do a 360-degree turn on itself and search for the ball at the same time. While searching for the ball, the robot will also take note on where the blue goal is and the yellow goal is too. If the ball was not found on the first 360-degree turn, the robot would move to the blue goal and do a 360 turn there and scan for the ball. If the ball was found, the robot would move to the ball and shoot. If the ball was not found, then the robot would move to the yellow goal, do a 360 turn, scan for the ball and shoot. If the robot had not found the ball in this 360 turn at the yellow goal, then it is assumed that the ball is not on the field. This was our solution to the problem of searching the ball.
It was a decision of the group to purely use vision as means of navigation. The robot would have to segment out colours and decide on the fly what to do with those colours. For example, the robot would have to avoid all objects of the colour black, and would have to be attracted to all objects of the colour orange, which represents the ball. To get the thresholding values, we had to run a series of tests. This involved using a camera that was supplied and the soccer field. As you can see here, this is an Excel spreadsheet of the values that were recorded. This describes the 3 main colour spaces that we investigated. It shows how each colour trends in those colour spaces, and ultimately was used as the thresholding values for the robot colour segmentation. As you can see, this is the actual segmentation of colours on the phone, what the robot is seeing in real time. These colours still need to be adjusted. However, I don't know, segmentation is pretty accurate.
Great work, guys. The robot looks brilliant. It did the task that we were assigned to do brilliantly. Looks like all the systems have integrated really well. Great teamwork. We've overcome a lot of obstacles. Very, very good work. High five, guys.
Yeah! I love obstacles.